Okay, so the overall goal of my 4 lectures, so 2 today, 2 tomorrow, is going to be parity violation at Jefferson Lab and beyond. And today's first lecture is going to be on electroweak interactions. So I just want to start, I'm sure that all the lectures give you some sense for this, but I just wanted to tell you, I have done summer school lectures before, and I am aware of a few certain things, such as student background and preparation varies. Some of you probably have had lots of nuclear and particle physics at an advanced level, but not all of you, so I don't want to assume it. You're going to get an excellent set of, you're getting an excellent set of pedagogical lectures on QCD topics. So these 4 lectures are a little bit, the first 3 lectures anyway, are going to be not much about QCD. As you complete your doctoral research and move on, you will learn to cope with imperfect knowledge on things unrelated to your own projects. And it's very important that you have at least a qualitative understanding of the breadth of nuclear and particle physics that is critical to select the interesting problems that you have to choose as you go on in your research careers. So disclaimer, I'm an experimentalist, so I will focus on measurements, but theory is critical. So I will be talking a lot about theoretical foundations at a very basic level, but I will be concentrating on the big picture, especially in the beyond standard model search field, which is my focus this morning. And I view this as necessary general knowledge when you're focused in other subfields. Okay, so the rationale for the lecture flow, today's and tomorrow's. Tomorrow's lectures are primarily about Jefferson Lab's parity violating electron scattering program. Okay, that's tomorrow's lectures. In order for those lectures, the motivation for these measurements and the unique capabilities and the impact of the physics measurements here at Jefferson Lab, it's important that you contextualize it. It is important that you know the foundations of electroweak unification in the standard model in general, and especially weak neutral current interactions, which is what the parity violating electron scattering program is about. So that's the first lecture. It's just going to be very basic electroweak physics. Then in the second lecture this morning, to understand one aspect of the parity violation program, which is searching for beyond standard model, one must have general knowledge of worldwide efforts in this arena. So that's what the second lecture today is going to do, especially as it relates to violation of fundamental symmetries. So I'm going to introduce the very basics of symmetries to begin with. So the outline of the lectures. So the first lecture this morning is Introduction to Electroweak Interactions, Precision Electroweak Physics, Electroweak Radiative Corrections, and the motivation for BSM searching. And later this morning, after the break, I will introduce discrete symmetries, historical discoveries using symmetry violations, and then kind of give you a broad brush whirlwind tour of various searches for accidental symmetry violations that are going on all over the world. All right, and then tomorrow's lectures, the first lecture will introduce parity violating electron scattering and the specific experiments that were designed to do BSM searches. Yeah. Oh, right. Oh, sorry. Yeah. So the third lecture is going to be on parity violation using for beyond the standard model searches. And then the final lecture tomorrow is how we will use parity violation to study nuclear and nucleon structure. Okay, so that's overall goal for this morning and tomorrow morning. And so now let's get started with the first lecture. So introduction to symmetries, this should be really a review for all of you. Electroweak interactions also, I hope, is just a review for all of you. And then finally introduce electroweak radiative corrections. And the QED part of this should be a review for all of you. But I will go through all of this, not assuming that you already know it. and then open questions and how this sets the scale for beyond the standard model. All right, so introduction to symmetry. So let's start. All of symmetry starts with Noether's theorem. I think you all know this. She said, if the Euler-Lagrange equation is invariant under coordinate transformation, there exists an integral of motion. This is the basis for everything we do. So for example, translational symmetry is related to momentum conservation. Invariance, time transformation is energy conservation, rotation is angular momentum, etc. But this is not just space-time symmetries, but it's also invariance of the Lagrangian or Hamiltonian that you're dealing with. And so, for example, charge conservation, if you take the charge operator, then you find that if it is invariant with time, then it commutes with the Hamiltonian, and it has very definite quantum numbers. Right? So that's how you get conserved quantities and quantum numbers. So this is all very basic stuff. So symmetry operations, group of all operations displays closure, associativity and have identity and an inverse. Finite groups are associated with discrete symmetries, infinite groups, continuous symmetry. And in physics, group operations can be represented by matrices. So ND rotations, so SO3 is equivalent to SU2. Invariant SU2 is angular momentum conservation, et cetera. So just a reminder. So continuous symmetry. So if you take the free particle Lagrangian, for example, you have UN invariance that leads to a conserved current, and then local UN invariance. You probably have dealt with already with local invariance in QCD, I suspect, in your QCD lectures. So this local U1 gauge invariance gives you electromagnetic interactions. And then in SU2 space, we call it isospin because of the historical connection to nucleon-nucleon interactions in nuclear physics. And so you have invariance in isospin space that yields 3 independent conserved currents because there are 3 independent Pauli spin matrices. Now we use the word weak isospin also in the standard model, and I'll come back to that later in the lecture. Okay, so the symmetries of the electroweak Lagrangian. The electroweak Lagrangian is SU2 left cross U1Y. Left stands for the left projections, Y stands for hypercharge. You have 4 conserved currents. Local gauge invariance yields 4 bosons, W plus, W minus, W0, and B0. And then after spontaneous symmetry breaking with the Higgs mechanism, you get down to SU2 cross U1 gets down to U1 electromagnetic, which leaves the photon massless. It gives mass to the W plus minus and the Z naught. Of course, you already probably gone through this. SU3 color and gluons gives you quantum chromodynamics. These are exact symmetries of nature. We believe fully manifest in the early universe. The thing to remember is that unbroken exact symmetries must have massless mediators and an infinite range force, such as the photon. Of course, the gluons are not infinite range for reasons that you already probably know. Okay. So this is sort of assumed knowledge, but what I'm going to do now is kind of tell you that the entire content of electroweak interactions can come, you could invent it without being Weinberg, Salam, Glashow, by just demanding that all interactions make sense all the way to high energies. Let me explain that by going to some very basic physics here. So let's start with quantum electrodynamics. Okay, so free fermion fields are solutions to the Dirac equation. So that's the corresponding Lagrangian. Local gauge invariance gives you the conserved electromagnetic current. And then you have Feynman rules for the emission and absorption of virtual photons by the fermion electromagnetic current. So now you can do a Feynman diagram. So here, let's just take electron-muon scattering just to remind you of all of the basic things that go into such a simple calculation. You calculate a matrix element. You have the 4 momenta. You have the 4 spinners for the 4 particles involved. You go through this calculation, you'll get a differential cross-section. This is the very basic electron-proton cross-section if the proton had no structure. So this is a very standard formula, but it all comes from this notation. So I'm just introducing this to give you the notation, okay? All right, so now the other thing that's important, the basic physics you're going to take before you're going to invent the standard model, is that the weak interactions are special in that they violate the parity symmetry. And so because it's such an important theme, it's going to occur again and again and again today and tomorrow, I'm going to take a minute to just give you the experimental basis for parity violation. How did we know first that parity is indeed violated? So C.S. Wu in Colombia, she took a cobalt nucleus, put it into into a cold trap, and had a magnetic field, and she observed that in this radioactive decay, the betas, the electrons, came out preferentially against the magnetic field. That was it. That's parity violation right there. She went up 2 floors to Li and Yang and told them that parity has been violated. Why is that true? Just because she saw that betas came this way and didn't go that way. So let's just remind ourselves what the parity transformation is. It's x, y, z going to minus x, minus y, minus z. This changes the sign of momentum, but does not change the sign of angular momentum or spin. Okay? So now let's just look at the vectors. The B field vector, the antineutrino going up with the spin pointing up, the electron going down with the spin pointing also up. These 2 spins have to point together because there is 1 unit of angular momentum that is lost when you go from cobalt to nickel. Okay? So these 2 have to align. If I now do a reflection, if I do the parity transformation, the B field vector will not flip sign, the spin vectors will not flip sign, but the momentum vectors will flip sign. And so you will end up with a right-handed electron and a left-handed antineutrino. That doesn't happen. Okay, so the fact that you have any anisotropy in the beta response with respect to the B field is parity violation. Okay, so we now know why this is true. This is important for us to understand that matter particles all have spin 1/2. So you can define a handedness or helicity chirality. I will tell you sometime later in the 4 lectures about the difference between helicity and chirality. For the moment, let's leave that alone. Feynman and Gelman proposed the V minus A form of the weak interaction, vector and axial vectors, and you'll see how I use that in the next slide. But the net result of it is essentially only left-handed particles can mediate doubly bosons, or right-handed antiparticles. So let me explain that in the next slide. Okay, so now weak interactions. So now let's do the same kind of matrix element. So I have now this 4 Fermi interaction, cobalt, nickel, antineutrino, electron, and I can write the matrix element this way. And what Feynman and Gelman proposed is instead of having gamma mu here, you have 1 minus gamma 5 times gamma mu. And so you have this situation, you have the 1 minus gamma 5 occurring here. This is the V minus A interaction because this is a vector and this is an axial vector. Okay, so why is this only left-handed? So just to remind you, for massless particles, if I make this projection, this is the helicity operator here. So in fact, these 1 minus gamma 5 is just the projection. 1 minus gamma 5 is the left-handed projection. 1 plus gamma 5 is the right-handed projection. These projection operators form a complete set. And so you really can rewrite this as just the left-handed spinners, left-handed projections of these spinners, and you don't need the 1 minus gamma 5. So this is the equivalent of what Feynman proposed, 1 minus V minus A, is the same as just saying left-handed projections are the ones that participate in the weak interaction. Okay? All right. So let me just emphasize about charge and handedness in the weak interaction. So electric charge determines the strength of the electric force. And what we mean by that is that you see diagrams like this, but you do not see this with neutrinos scattering. Neutrinos cannot emit a photon, a virtual photon, right? So they don't have charge. Likewise, right-handed particles or left-handed particles or right-handed antiparticles have weak charge, and so they can emit a virtual doubly boson, but the left-handed antiparticles or right-handed particles cannot. Okay? So now, important, helicity is not equal to chirality when you have massive particles. We tend to use helicity and chirality. We mix and match because we are typically dealing in the high energy regime where the mass can be ignored. But it's important to remember this, that the helicity operator commutes with the free particle Hamiltonian. So it is conserved, but it's not Lorentz invariant. So you can just think about it. If I have a massive particle, you observe it spinning. You can always observe it spinning the other way because you can race past it and look at it from the other side. So it's not Lorentz invariant. On the other hand, the chirality operator is not conserved by the free particle Hamiltonian, which means that if I have a free particle left chiral projection, it will ultimately develop a right chiral component, right? And this is very important for neutrino oscillations, for example. Okay, so, but it is Lorentz invariant. Okay, so in fact, when you talk about weak interactions being left-handed, it's actually left chiral. It's the left chiral projection that can emit doubly bosons. Okay, so that's about electromagnetic and weak interactions. Okay, so now we are ready to do the thought experiment that will invent all the particles, the W and the Z bosons. So let's start with the muon decay matrix element. And you can just very easily calculate, this is the only dominant decay. So to get the muon lifetime, you just calculate this matrix element, and then you can get the partial width, and then from the partial width, you can get the lifetime. It's important that all of you know how to do these simple calculations. So if I look at this, h bar c is 1, you should know that this has the units of energy. And then by using a conversion factor, you can quickly get to, and putting the appropriate amount of h bar c's in there, you should be able to get this in time. Okay, so it's not, I'm not going to do it here, but it should be something everybody should know how to do. Okay, so now let's do a thought experiment. I'll take the same matrix element, which I now know exists because I've measured the muon lifetime. And then I can now construct this Gedanken experiment, the luxury of being a theorist. You can come up with an experiment which can never be done and still talk about it. So I can take, let's imagine I can make an anti-neutrino electron beam and collide it with an electron. It should be possible then, if you made such a hypothetical experiment at high enough energy, that it will produce occasionally an anti-muon neutrino and a mu minus. Okay? And the thing is that it requires the same matrix element. And then you can now generate a cross section for this with this matrix element, and you get this G Fermi squared E squared over 3 pi squared. So this is something people calculated in the early 50s. And then they knew that the Fermi theory does not work at high energy. So you've heard this probably all the time. Fermi made a nice theory, doesn't work at high energies. This is the reason, right? When E is a TV, probability is greater than 1, okay? So they all knew how to fix this. They knew how to fix this, and they fix it by having a massive mediator, right? So now I can redo the calculation for a massive mediator, and I will get this term that the mass of the mediator is related to G Fermi in this way. Okay, and now I can do this calculation, and I get 4e squared over 4 times e squared minus mw squared squared. So when e is low, you get this, and when e is high, it goes like 1 over e squared, no problem, right? So they knew that the mass of the W had to be between 10 and 100 GeV, and that also automatically explained why the weak interactions have short range. It has nothing to do with anything like the strong interactions or self interactions or anything like that. It has to do with the fact that when you have a short range interaction, then the mass makes the range decay away, right? So that's the reason. Okay, so now people knew that you could do real W production in PP bar collisions. They realized that they needed a collider. The collider was invented at CERN. They could calculate what the partial width should be, what the total cross section should be. I'm not going to go through this, but in fact, this logic was used to propose the PP bar collider at CERN in the 80s. And then the UA1 experiment discovered the W boson, right? So the point is that by simply asking for the fact that the cross-section has to be well behaved at high energy, you could invent the W boson. All right, let's go on now and do more thought experiments. So let's imagine that you could collide a positron with an electron neutrino, then occasionally you should be able to produce a W plus and a photon. Okay? Write the Feynman diagram for that, and then you immediately realize this will blow up, and that you at least need this diagram here, where the gamma couples to the W. Okay? And then this cross-section becomes finite. I won't prove it to you, but take my word for it. So unitarity violation forces important constraints. So you now need the WW gamma vertex. This is a non-abelian vertex, a very nice, beautiful new thing in the standard model. And then if you now think about E plus E minus goes to W plus W minus, it turns out that that also blows up unless you have this diagram with the Z naught. You have to invent a neutral mediator, the Z naught, and you need the Z naught W plus W minus vertex. And if you put all three together, then this cross-section also is finite. Okay, so now you have forced to invent the Z boson in order to make this work. By the way, this was, of course, proven in real experiments in the mid-2000s. I'll come back to that at the end. Now, finally, if you take longitudinal vector boson scattering, ZZ goes to WW. Now that you invented these particles, it turns out that this blows up unless you have something like this with a spin zero boson mediating it. So you're forced to invent these couplings. And not only that, you find that in this, there is one free parameter that is introduced. And it's this diagram that forces you with this constraint that finally brings together the mass of the W and the mass of the Z with the weak mixing angle. Okay? So all I've demanded here is that these cross sections, everything that should be possible to measure, makes sense all the way to high energy. That's all. So you didn't really need to be to know all of the fundamental things that Higgs, Glashow, Weinberg, Salam all had to invent in order to come up with the standard model. In fact, they knew it had to be right because of these arguments. Okay, so this is a very famous plot. This is at this point about 20 years old. It shows you the center of mass energy in E plus E minus collisions versus the cross section from few GeV to 210 GeV. These are the low energy, early low energy E plus E minus colliders. The J psi is sitting somewhere here. Then you had people who are trying to find the Z boson, all of this. They really thought in Japan and Tristan that they would find it. But by then, the weak mixing angle had been measured, and we knew that we needed to get to 90 GeV to get to the Z boson. And that immediately motivated the the SLC and LEP colliders to get to this. And you can see the Z resonance here at 90 GeV, which is what is expected because by then we knew what theta W and MW were. And then very importantly, when LEP was able to upgrade their energy to 200 GeV, you come down here to W plus W minus threshold, and then the fact that this cross-section doesn't blow up tells you that these diagrams exist. Okay, so this is very important that these, this is the E plus E minus W plus W total cross-section, and this is the inclusive cross-section, and this is for W's. Okay, so the fact that this determines that in fact these diagrams exist. Okay, so that's sort of the overall picture of electroweak interactions. So to summarize, we have the particle content of the standard model. We have the electromagnetic charge, the W charge. This is the plus minus 1/2 weak isospin charge for the left projections. And then the right projections have isospin 0. And then the Z charge, according to electroweak unification, goes like T minus Q sine squared theta W, T being the weak isospin, Q being the charge. And so you can now assign the left and right projections of each of these particles depending on its weak isospin and its charge. And very important to notice that the Z couples to both the left and right-handed projections, whereas the W couples only to the left-handed projections. And in the jargon of the field, instead of talking about the left and right-handed projections, we tend to talk about the vector and axial vector couplings, which are just the sum of the left and right-handed couplings is the vector coupling, and the difference between the left and right-handed couplings is the axial vector coupling. Okay? All right. I think before I get to radiative corrections, I'll ask if there are any questions. Okay, so let's get to radiative corrections. So again, the QED part should be, this is how experimentalists think about radiative corrections, okay? So you can just see how, what our argument is. So the idea is that from Feynman rules, you should be able to construct all possible diagrams consistent with known conservation laws. So for example, if I look at E mu scattering, then the outgoing muon can emit a photon, then the intermediate photon can emit a fermion pair and get reabsorbed. The amplitude is the sum of all possible states. This is the Feynman's path integral formulation of quantum mechanics. The problem is when you start doing this, the whole amplitude diverges. You get infinities, well-known problem. So to put it systematically, just take one diagram, this vacuum polarization diagram. You take this, you add this, you introduce this parameter, sigma gamma gamma q squared, which is this amplitude for the vacuum polarization, and you end up with this. Now what you do is you replace E squared here with this E squared plus sigma gamma gamma q squared, okay? That's still infinite, but you hold on. Now consider another diagram, which is E plus E minus going to mu plus mu minus, okay? That also has a vacuum polarization, the same thing, but it's slightly different because this is now an annihilation diagram, and we'll call that pi gamma gamma q squared. So the idea is that you now replace E squared with this, put it in here, and you end up with the difference between pi, I screwed up here. It's pi minus, pi p squared minus q squared, and it turns out that this is finite. Okay, so the point is that you can only do a calculation when you already have done a measurement of the fundamental coupling to begin with. So let me summarize that in the next slide. So the way it works is Feynman rules with electric charge, so QED. So again, you calculate sigma 1, the test process, which is E mu scattering. Let's say you make that measurement. From that measurement, you get the electromagnetic coupling. You take that measurement, measured electromagnetic coupling, and you stick it into sigma 2, which is the new process you want to measure, and that is finite. Okay? So not all quantum field theories behave this way, but the ones that are renormalizable theories do. And so the big deal for the electroweak theory, the SU2 cross U1 theory, was that that was proven in the early 70s by Tuft and Feldman. And then for QCD, of course, you know a lot more from your QCD lectures. This was proven by Gross, Politzer, and Wilczek. So what is happening here at the QED case anyway is that this kind of vacuum polarization diagram can be understood in the fact that the fine structure constant, the coupling constant for electromagnetic interactions, is actually getting smaller at increasing distance. Now, again, this is different for QCD. This is the QED case. So the effective charge increases with decreasing distance. And these are higher order terms. And the way to think about it visually is that the charge is sitting in a dielectric, and so depending on what Gaussian surface you use, different amount of charge is enclosed, right? So that's how you think about it. Now, in fact, you can do a proper calculation of this. The shift in the running coupling can be determined analytically for lepton loops and by a dispersion integral for the hadron loops, because this is non-perturbative QCD. And so what you do is you cut this diagram and then use the optical theorem, and then you use the experimental data, E plus E minus to QQ bar, normalize it to E plus E minus to mu plus mu minus, and then you're able to do this calculation, and you can show that, in fact, alpha moves in exactly this fashion, right? So this is the running couplings. Okay, so all of this is essentially introduction, and I think what I'm now going to show you is how running works for the electroweak theory is probably new. How did we prove it? So this is one of the big deals that happened in the 90s once you had a lot of data from the Z resonance. Okay? So let's summarize again what the electroweak theory is. So you have, this is just a reminder. So this is now how you think about it. I showed you why you needed these particles and these couplings from first principles, but in fact, what was invented was these relationships, okay? So this is just a summary. Now, let's look at electroweak theory at one loop. So now let's apply the same principle that I did for electromagnetic interactions, E mu scattering, E plus E minus annihilation. So what you need to do for the electroweak interactions is that it's SU2 cross U1. So you need 3 inputs instead of one. For electromagnetic interactions, you just needed 1 input. So the sigma 1, right? Here you need 3 inputs. So these 3 measurements here are used as input. Again, you need 3 measurements, not just theoretical constructs, theoretical couplings. You need actual experimental measurements. So the electron G-2 anomaly is the most precise way we know, to like 12 significant digits, to calculate alpha QED. So the electron G-2 is an actual experimental measurement of the G-2 precession of the electron. These are atomic physicists who do these amazing experiments. And that is the electron G-2 anomaly. That's your first input, alpha QED. The second input is G Fermi, and the simplest way is the muon lifetime. So you have this ultra precise measurement of the muon lifetime. You get an effective G Fermi from that, which has all the loops and everything in it. And that is your input, second input, G Fermi. The third input is the mass of the Z boson. And again, that is just, you measure the physical mass of the Z boson by measuring the Z line shape, which is back to this picture here. So you actually do a bright resonance, bright Wigner resonance fit to this shape, and you get the mass of the Z from that. Okay, again, it contains all the loop effects in there because you're making an experimental measurement. That's your third input. Okay, so now, once you have these three inputs, then you can look for the fourth and fifth measurement, and now you can test the standard model. Okay? Now remember, MW is the mass of the W that's measured in the colliders. Sin square theta W is looking at Z production or measuring it at low energy, whatever. These are experiment 4 and experiment 5. I want to emphasize again that these are not theoretical inputs. This is experiment 1, 2, and 3. And that becomes the input to the standard model. You can't use these experiments to test the standard model. You need it as input to the standard model. Okay? It's very important separation there. Okay, so now weak mixing angle, there are many definitions. Now, once you talk about radiative corrections, the simplest definition is 1 minus mw squared or mz squared. This was what was used in the early 70s onwards. But then in the 80s, people began to realize that the top mass is very heavy. And it turns out that there's an enormously large radiative correction that occurs here that makes the theoretical errors blow up because the top mass is so heavy. So this became disfavored. So when the Z resonance data was taken, they decided to just call the mu coupling, the muon Z coupling, which goes like 1 minus 4 sin square theta W, and just use the muon Z coupling and then make this calculation and call that the weak mixing angle. Okay, so this is 1 minus the muon ZZ coupling divided by 4. This is very good, but once you start to test experiments at other scales, there were some very nasty theoretical problems. Okay, so the accepted definition nowadays is the so-called sin square theta W ms bar. It's theoretically motivated, but it's very important for experimentalists to remember that this is not a physical quantity. And for each process, you have to actually have collaborative theorists figure out, they'll tell you what sin square theta W ms bar is at your experiment, and then you have to go and get the physical prediction for your experiment, case by case. Okay? Now, it's an important note for us experimentalists. We shouldn't worry too much about these definitions when we are trying to design a new experiment. When designing experiments, all that matters is the projected uncertainty. So the actual value doesn't matter. It's just the uncertainty. When the experiment is fully designed, then you work with theorists to extract the correct answer. Because that's how it works. So you don't really need to obsess over or getting the definitions right when you're trying to design new experiments. Okay. So now this is the crux of electroweak radiative correction. So I'm going to go slowly through the slide. So I first put down there are numbers in here that I'm going to show you that has 20, 30 years of work from many, many theorists, many, many experimentalists, many, many experimental collaborations. So here are the main formulas. G Fermi, fine structure constant, and then the famous electroweak mixing angle, two formulas. Okay, this is how you get the two formulas, one from the electroweak unification and the other from the Higgs mechanism. So now the key are these approximate signs here. Why are they approximate? Because they're only true at tree level. When you go to radiative corrections, this deviates due to higher order terms. And so to test the standard model at the level of electroweak radiative corrections, you're going to see the deviation from this equation. In the jargon of the field, this is called delta R. Okay, so you can construct three different delta R's depending on whether you use MW, MZ, or sin square theta W. Only need two of them. Once you have MW, MZ, sin square theta W, once you have two of them, the third one is predicted. So you use two of them. So if I use MW and MZ, which is this equation, if I use MW and MZ, that's this equation, I get that the deviation from 1 between this is about 3.5%. Notice that this has been measured to 1% of itself. This is a 3.5% effect of this equation deviating, and it is being measured to 1% of itself. There are extraordinary efforts on how precisely MW and MZ have been measured, and G Fermi. Here's a theoretical prediction, and this theoretical prediction is shown in this way to show the dependence on the Higgs mass. We now know that the Higgs mass is 126 GeV, 125, 126, thereabouts. And so if you put this to be that, then this goes to 0 with the standard model Higgs. And so this is what you compare to that. Look at this extraordinary agreement between these two, right? And so the fact that we can calculate at this level with this precision, there's a little bit of uncertainty from the running of alpha S and the mass at the top, but that's it. Everything else has been extraordinarily well calculated by phenomenologists. Okay, so now you can do the same thing with sine squared theta W and mz, which means I'm using this equation. And then I'm also using this equation, and I get this 6%. And again, you can see the agreement. And finally, you can use sine squared theta W and MW, and forget about mz. And you end up with this equation. And again, the agreement is amazing. So this allows you to extract a theoretical prediction for the MW and compare it to the actual measurement, or the theoretical prediction for sine squared theta W and compare it to experiment. These are all extraordinarily good agreement. And in order to get this agreement, if you assume you don't know the Higgs mass, this is what the Higgs mass was predicted to be. So all of this was known by the mid-2000s when LHC came online. Okay, this precision here probably was a factor of 2 worse when LHC came online, but they kind of knew this. So there is a very famous plot, this plot here, that comes from the community of phenomenologists who do electroweak radiative corrections using all of the LEP data. So this is showing the Higgs mass and the chi-squared of all the fitting. And this is a famous plot. This is 2008, I think, circa 2008. And this yellow line is Higgs mass has already been excluded up to 110 GeV or so. People are getting nervous. This is the only window here because they said that the Higgs cannot be heavier than 150 GeV. So that's the situation when LHC came online and the Higgs was discovered. This animation won't work here. Maybe at the end of the talk, I'll put it up because we downloaded the animation. But the famous plot is this is the standard model background for Higgs going to 4 leptons. Okay, so this is the Z resonance. This is 2Z production here and some background, UCD background. The Higgs showed up right here. Okay. So it also showed up in Higgs to gamma gamma at the same mass, which is a good thing. And so this is an extraordinary triumph of electroweak physics, theory and experiment. I want to emphasize again that the Higgs mass, a spin zero massive particle to generate mass, was proposed for theoretical reasons. And the fact that we actually got the Higgs mass where it was predicted to be, is an extraordinary achievement of both experiment and theory. Okay, so the way you typically look at this in the particle data book is by looking at plots like this. So these are classic global fits of all the experimental data. So this is, for example, MW versus M top. The green bars are the actual physical measurements of these quantities. And this, for example, it shows you the line in the standard model for 600 GeV Higgs, 300 GeV Higgs, 125 GeV Higgs, et cetera. And then the gray band here, does not use MT, MW, or MH and everything else. The fact that you end up there is kind of amazing. It has nothing to do with these three quantities, and it gives you a band like that. Okay, so it's remarkable. Likewise, you can look at MW versus sine squared theta W. So this is the world average sine squared theta W. This is the MW. And then this blue is the prediction of the standard model for 125 GeV Higgs. And the fact that the blue and the green overlap this way is an extraordinary thing. And then finally, if you look at M Higgs versus M top, here's where the Higgs mass is that we have discovered. Here is M top. And again, these different bands show you the indirect measurements of these quantities. Okay. So this is why we believe in the electroweak theory and the electroweak interactions. So I call the Higgs discovery bittersweet. Why do I say that? So all of this is now completely well understood, right, at the level of quantum corrections. But I call it bittersweet because I personally, I was one of the, I used to get into arguments with my stern colleagues. I was going to say, I wish you know, can you just rule out that window completely? Because then it'll force us to go back to the drawing board. And that's why I call it bittersweet, because this amazing victory that we have had has left us with all kinds of questions, and we have no idea how to proceed now, right? So there's no guidance on where to look because everything works perfectly, right? So one has to take a very broad approach to make progress. And so that is where the field of the intensity frontier. It's a complementary experimental strategy for BSM searches to be as model independent as possible. And this is my classification, and I'm going to go through in the next lecture, the first three of these, okay? So I'm going to just lay out the basic idea, theoretical idea in the last, I'll take 5 more minutes. So the basic idea of the intensity frontier, again, I'll come back to all of these in the next lecture, is that there are new dynamics. Here's a standard model Lagrangian, and then there are higher dimensional operators. You can systematically expand the higher dimensional operators. And because we have no guidance, we have to look at everything. We have no guidance, so look at everything. We do believe there's new physics out there, and for reasons I put down in the previous slide, right? I just said we have all these questions. So you can choose your favorite question, and you try to pursue that in an experiment. So all the measurements you're pushing all experimental parameters to the extreme, whether it is intensity and luminosity in an accelerator, volume, radio purity in an underground experiment, resolution, precision, accuracy. You're just pushing to try and get to these sensitivity to higher dimensional operators. And in most cases, observers exploit a symmetry principle, so it's important to understand symmetries. So what we are doing here in particle physics, we are trying to get to smaller and smaller length scales, which means earlier and earlier in the universe. And in nuclear physics, we are trying to understand how things are built, because at the level of a femtometer to an autometer, we know everything, right? And then we need to build more complex objects. We do that in nuclear physics. And we need to understand these other things that are going on probably at very high energies. Okay, so this is, I'm channeling a good colleague of mine, Vincenzo Cirigliano. These are slides stolen from him. How do you make a general BSM effective field theory framework? So you need to describe physics originating at very high energy scales, much higher than the scale of electroweak symmetry breaking. And so you have all of these build operators out of standard model fields, impose Lorentz and standard model gauge symmetry, organize operators, power counting. And then here's the main thing I want to communicate. You look for 2 classes of operators. One is violating an approximate or exact symmetry of the standard model. So here are examples. I'll talk about some of them in the next lecture. And then these are what I'm going to talk about tomorrow with parity violating electron scattering. Operators that give corrections to standard model allowed processes. So muon G minus 2 and parity violating electron scattering are good examples of this, where you have precision predictions that you can test against experiments. So this is all, the theorists have to do extraordinary amounts of work to connect new physics to low energy. You have to build a tower of EFTs. And the standard model effective field theory is a standard model BSM link. When you come down to lower energies, there's a lot of nuclear physics that you have to do. Okay, so this is the intersections of nuclear and particle physics. So I just want to end by saying that as an experimentalist, you look at all the probes that are out there when you come up with an experimental idea. Electron beams, muons, kaon, pion beams, neutrino beams, neutrons, underground detectors, nuclei. Okay, so I've just put it down here, what each of them can do, JLab, MINDS, EIC, kaon, pion beams in these places, neutrino beams, neutron beams, and then various underground detectors. And then, of course, weak decays in nuclei, FRIB, and so on, and tabletop. Okay, so all of these is, again, looking at the BSM framework, you're trying to isolate different parameters that you can chase after. So it's very important that you know what else is going on so that you're not chasing after the same parameter that someone else is doing, right? Okay, so this I'm going to talk about more in the next lecture. So it's 5 minutes to 10. I think we should stop here. So I will summarize. Sorry, I've been moving around. Symmetries and conservation laws, powerful conceptual avenue to synthesize our current understanding of fundamental interactions and how to channel our creativity for new discoveries. Electroweak interactions. Since the 1990s, we have made enormous progress in understanding electromagnetic and weak interactions at extraordinary precision. We now have a complete verification of physics at the scale of electroweak symmetry breaking, including Higgs boson interactions. And BSM physics, there is a worldwide systematic push to search for new physics using a large and varied array of experimental techniques. Right? Thank you. Oh yeah, you can just put that up and it can move. It's something I stole from one of my colleagues. I probably am violating some copyright laws, but we can see it here. That's fine. So any questions? We can take a small break before we go to the next thing, but yeah, so here it is. This is how the data came at when LHC turned on. You can see the background. Now you can certainly see at 125 GeV new points. And that's where they showed up. So that was the first discovery. Yeah, sure. You could click on it again. It'll come back. Yeah, there you go. Yeah.
Oh, there's a question.
Yeah, go ahead.
Yeah. So I mean, this explains why the Higgs, why we need like a spin zero boson at these energies. Where exactly does this idea of it like coupling to like mass or something like that come from?
That's why Higgs originally proposed it. But what I'm just showing you is that he came up with the idea because the theory wouldn't make sense without it.
See, yeah. Okay.
I mean, so if you needed the original thing, when I showed you, actually, let's go back to my slides. Is that okay?
Yeah.
Yeah. So if you go back to before I started this thing about Gedanken experiments, let's go all the way back. It'll take me a minute. Yeah, let's go back. And the way I put it down, this is the way Peter Higgs' mechanism is shown, is in this slide. The idea is that in order, they knew that W had to be massive. And so if you wanted to unify SU2 cos U1 and you wanted massive bosons, then you needed the Higgs mechanism then you take 3 degrees of freedom and give mass to W's and C's.
Okay, gotcha.
And then giving mass It was the minimalist approach to give mass to the fermions using the same
Right.
mechanism.
Right,
It
okay,
was originally just for giving mass to the bosons.
okay, gotcha. Thank you.
Other questions?
In fact, the issue of fermion mass is why we are so excited about double beta decay, which I will talk about in the next lecture.
You mean like neutrinoless double beta decay specifically?
Yes, yes.
Gotcha.
I will spend quite a bit of time on neutrinoless double beta decay in the next hour.
Very nice, very nice.
More questions or more coffee? It's 15 minutes.